So in 9-5, I know it says review, but ignore that. In 9-5, we're going to be looking over testing two variances or standard deviations. But this is testing two, and we'll just say variances, because that's what we'll hopefully be using most. As we're doing this, there's something really important to know about this. We've done variances before. Specifically, we looked at the sample variance compared to the population variance. And when we did that, we used a chi-squared test. But this time, we're actually comparing two different sample variances, or two different population variances. And I think really all this is just samples. So we'll just focus on the samples. And because we're focusing on two samples, not one sample, one population, we're going to change our test. And really, now we're going to be using a F test. An F test, the letter F as in fox. Okay? So it is not a chi-squared. All right, so you need to make sure that you know this is not going to be a chi-squared test anymore. It's going to be an F test. Okay, and again, the reason is because a chi-squared test, it compares a sample to a population. Okay, but an F test, it just compares two samples. Compares two samples. Okay, and I'll show you how to use the F test in a second. There are some characteristics that I do need you to know. One thing, so we'll say characteristics. One thing you need to know is that you cannot have a negative F. So F cannot be negative. All right. The second thing is that it is, again, positively skewed, or it is a right skew. All right. And then the third thing is that the mean value of F is approximately equal to 1. And we'll talk more about that in a second. And then finally, it is a family of curves. Okay, we know this one already. It's a family of curves based on the degrees of freedom. The degrees of freedom. Okay, and we'll talk about the degrees of freedom not extensively, but pretty for a little bit. We will definitely talk about the degrees of freedom, because now we're going to differentiate between the degrees of freedom of a larger sample and a smaller sample, and of a larger variance and a smaller variance. And so we'll talk about that in a second. But what is the formula? Well, the formula is going to be F equals the variance of the first divided by the variance of the second. Okay, so this is a very straightforward formula. It's not super difficult, and some things you need to know about it is that this right here is what, no matter what, it's your larger variance. So if they give you your information, quote unquote, out of order, that's okay. As long as you remember that the larger variance goes on top, then we're good. And therefore, if that is the larger variance, then whatever the sample size sort of goes with that numerator as well, and we'll talk about that I'll show you how to do that in a second. So if the larger variance has to go on top, that means the smaller variance needs to go on the bottom. Okay, so things to really know about this is that you might have to ignore the order, okay, in order to make sure that you have the larger variance on top and the smaller one on the bottom. The other thing is that your degrees of freedom, and actually we'll just do an example so that we can see clearly what we're doing here. So here is an example. All right, we have find the critical value of a right-tailed F test where alpha equals 0.5 and the degrees of freedom for the numerator which I'm going to just write as df capital N, so you know that's degrees of freedom of the numerator, are 15, and the degrees of freedom for the denominator are, which is dfd, is 21. All right, so I'm going to go to the table to find the critical value. All right, I'm going to go to the table to find this critical value. All right, and I went ahead and added it to our teams. So if you go to teams and you go to, well, first I'll have to be in our class, so one second. Okay, so once again, here is our class. If you go to the very top, we have files right here. We're going to click on that. And now we have, or should have, all of our scores right here. I added one called the F score, and you can see it's new because it has this little, annotation next to it that represents that it's new. So I'm going to open that up, and it's going to bring me open to a PDF. Now the PDF is a little hard to read in this format, so if you press this button right here, this tells us to rotate it. So I'm going to click that, and now it's a little bit easier to see. If you want to maybe make it a little bit bigger, you can. Let's say I want to make it 125, whatever it is. Okay, so our degrees of freedom, or our alpha, was 0.05. So I'm going to look for the alpha at the very top, 0.05. This is 0.005. So I'm going to scroll down until I get the correct alpha, which for us is going to be on the 4th page. All right, and it said that the degrees of freedom of the numerator was 15. So that is across the top. All right, that's going to be my 15 right here. And then my degrees of freedom of the denominator is 21. So I'm going to scroll down. Oops, not very good at scrolling down. So I'm going to scroll down until I get to 21, which looks to be right here. All right, so this is my value, 2.18, and that's how you find the degrees of freedom. All right, so degrees of freedom is going to be 2.18. Do the same process again for the next one. It says find, what's this one down here? Find the critical value for a two-tailed test when alpha equals 0.05 and when the sample size from which the variance for the numerator was obtained was 21 and the sample size from which the variance from the denominator was obtained was 12. Okay, so there's a couple of things going on right here. The first thing is that we have a two-tailed test. All right, anytime you have a two-tailed test, you need to take your alpha and you need to divide it because that's how you do. So our alpha is really going to be 0.025. The other thing is we have information about the numerator. Okay, it says the numerator had a sample size, that's n, of 21, and the denominator had a sample size of 12. Well, that's our sample size, but not our degrees of freedom. So remember, our degrees of freedom is going to be n minus 1, so that'll be 20 here. And our degrees of freedom for the denominator is going to be 12 minus 1, which is 11. All right, so now I can go to my screen, and my degrees of freedom of the numerator is 20, the denominator is 11. So let's look at that. All right, first things first, I need to make sure my alpha is in the correct, I'm on that correct page. I'm not, so I'm going to go up. Now it's 0.025, which is what I do need. All right, the numerator was 20, so that'll be right here. And my denominator was 11, so that's going to be 3.23. All right, so I'll write that here. Critical value is going to equal 3.23. All right, so that is how you find your degrees of freedom. We're going to do one more. What if you look closely at the PDF that's on Teams, unfortunately you'll notice that there are some breaks, like it goes from 15 to 20 on certain locations. And so because of that, what do you do if it tells you a degree of freedom of the numerator and they don't actually have that number? So the next example is going to be like that. We have find the critical value for a right tail test when alpha equals 0.05, and the degrees of freedom for the numerator is 18, and the denominator is 20. All right, so whenever this happens, a good rule of thumb, is to use the closest smaller value. So if your degrees of freedom is not listed, use the closest smaller value. All right, and that's pretty straightforward. So I'm going to go to my list. Okay, my degrees of freedom was 0.05. It was a right tail, so I'm going to go find that. I don't have to divide it. And degrees of freedom for the numerator is 18, but if we notice, 18 is not listed. We got 15, we got 20. So I'm going to pick the closest smaller value, which is 15, and then my degrees of freedom for the denominator was 20. So I'm going to scroll all the way down until I get to the 20, which looks to be right about here. So my value is actually using a degree of freedom for the numerator of 15, and my critical value would end up being 2.20. So I go back here and I would write that. Critical value equals 2.20. All right, so here's an example. Now that we've sort of practiced finding our critical values on our F table, which we've never used before, we're going to go ahead and do our first example. So it says a medical researcher wishes to see whether the variance of the heart rates of smokers is different from the variance of heart rates of people who do not smoke. Two samples are selected and the data are shown. Using alpha equals 0.05, is there enough evidence to support the claim? Assume that the variable is normally distributed. All right, so first things first, if I look at my table, I just want to go ahead and highlight the bigger or the biggest variance. All right, my biggest variance is this one. So because it is the biggest, I know eventually that's going to go on the numerator. So that's good for now. I will go ahead and put degrees of freedom of the numerator, and this actually is going to be 25 because it's n equals 26, and degrees of freedom is n minus 1. And so this will be my degrees of freedom of the denominator, and it'll equal 17. All right, I just wanted to do that right off the bat, and now I'm going to go ahead and go through my steps. So first things first, my null hypothesis. My null hypothesis is when my two variances are equal. And remember, we're making assumptions or we're making conclusions based on the population, which is why instead of using S's, like what I have down here, I use O's. All right, so then my alternative, I'm looking at my information. It says it wants to see if it is different. If it is different. I don't see anything about less than or greater than, so I'm going to go ahead and put this as does not equal, which makes it a two-tailed test. And this is my claim. So if I were drawing my little box, I could automatically cross off any of the null hypotheses statements. All right, now I can go ahead and find my critical value, which is based on an alpha. Take my 0.05. It's a two-tail, so I'm going to divide it by 2, 0.25. And again, I have my degrees of freedom of the numerator is 25, and the degrees of freedom of the denominator is 17. So I'm going to go to my table. All right, here is my table. See if we can get this. All right, I am not on the right alpha, so let me scroll up. Now I am. Okay, my degrees of freedom for the numerator is 25, so if I go up to the very top, I have 25 in between the two, so I go to the closest smaller value, which is 24. And then my degrees of freedom of the denominator is 17, so I'm going to bring this down and find 17, which is right here. So 2.56 is my critical value. 2.56. So let me write that down. Critical value equals 2.56. All right. Now that I'm done finding my critical value, I'm going to find my test value. All right, and remember we're using the formula, the variance sub 1 divided by the variance sub 2. All right, I have all that pieces of information from my table, so I'm just going to plug in my numbers, 36 over 10, which is going to give me an answer of 3.6. And if I were to draw my picture, and really my information is, it's not quite like that. It's skewed, remember. Okay, so because it is skewed, let me erase that a little bit. Because it is skewed, I know that my 2.56 is going to be 2.56 right around here. And so that means if I were to shade in my piece, it'd be here. And really there's shading going on over here as well, because it's a two-tail. But I'm going to take my test value. 2.56 is to the right of 3.6 is to the right of 2.56, so it would be somewhere around here, 3.6. It is in the shaded area, so I know I would reject the statement. And so my statement would be, there is enough evidence. There is enough evidence to support the claim. And that is my answer. All right, so let's do one more. So this says a researcher selected a random sample of 10 psychology graduates and found that the standard deviation of their grade point average was 0.72. Then she selected a random sample of 14 engineering students and found that the standard deviation of their grade point average was 0.51. And using alpha equals 0.10, can we conclude that the variance of the grade point averages of the psychology graduates is greater than the variance of the grade point averages of the engineering students? All right, so first things first, we can set up our hypotheses. The null hypothesis is when our two pieces are equivalent. All right, and our alternative is going to be when the first little bit is greater than my second piece of information. And this is what we're testing, so I'm going to put my claim right here with the alternative hypothesis. And now I'm going to create just a quick little table so that I have all of my pieces, just like how I did with my with the previous problem. I'm going to set up a table so that I know what piece goes where. So I went ahead and just put all my psychology information together, and I have written down the sample size, which was 10, and I went ahead and subtracted 1 for the degrees of freedom. The other thing that it gave me for psychology was that the standard deviation of the grade point average was 0.72, which is great, except I don't want to use the standard deviation. I actually want to use the variance. So when you have standard deviation, just go ahead and square it so you can get what you actually need to plug in. So I'm going to go ahead and do that. And now I'm going to do the same thing with my engineering students. All right, so I went ahead and wrote all my pieces of information. I can easily see from here that the psychology department has the larger variance, and so because of that, that's going to be end up being my numerator. But let's go ahead and just pause for a second and find our critical value, which is the next piece. Critical value, again, is based off of alpha. It is a one-tailed test, so I don't have to worry about that. All right, so alpha equals 0.10, and I have all my pieces, so I'm going to go ahead and go to my F table on Teams to get all of this. So our alpha is going to be 0.10. We see that we have our alpha at the correct location, and we are going to find our degrees of freedom of the numerator, which is going to be 9. All right, 9, which is right here. And our degrees of freedom of the denominator is going to be 13, as we said before. So we're going to go down to about, went too far, 13, which looks like it's going to be 2.16. So 2.16 is going to be our critical value. If I want, I can go ahead and draw my picture, but I'm going to wait till the very end. Now I need to find my test value, which is F equals the variance over the large variance over the smaller variance. I said earlier that our larger variance comes from my psychology department, so it would be 0.5184 divided by 0.2601. We can type that into the calculator. And we should end up getting 1.993, but I'm just going to go to 99 because my critical value is at 2 decimal places, so I want my test value to also be at the same sort of rounding rule. So I can draw my picture, which will look something like this. All right, my critical value I said earlier is going to be at 2.16. Take my test value. My test value is a little bit short of that. It's 1.99, and it is not in the shaded region, so I would not reject. Don't reject. All right, which would be the statement down here. If you write it out, it should say there is not enough evidence. There is not enough evidence to support the claim. And remember, the claim was that the psychology grade point averages was larger than the engineering, So that is how you are going to do these problems. If you have any questions, please make sure you are texting me on Teams. Teams is really nice because I'm able to call you if need be, and I can share my screen with you so I can show you the steps. It's very helpful. So please make sure you are texting me and using those resources. Good luck and have a great day.